Hello again. In the last video we talked about De Moivre's theorem and we proved De Moivre's theorem. In this video we're going to be applying De Moivre's theorem. We're going to apply it in this problem. Express cosine of 5 theta in terms of cosine of theta. So it's not maybe immediately obvious how we can approach this problem, but how can we use De Moivre's theorem? So what we're going to do is we can write it as cosine of 5 theta plus I sine of 5 theta. This is what is typically the right-hand side of De Moivre's theorem. So we can actually, using De Moivre's theorem, we can say that cosine of 5 theta plus I times the sine of 5 theta, we can say that that equals cosine of theta plus I sine of theta to the 5th. Well, what we want is to express cosine of 5 theta in terms of cosine of theta. And so now we need to expand this monster. To do that, we could just bash it out. First we do squared, and then thirds, and then fourth and fifth. Another way to do it is actually use Pascal's triangle. And really, Pascal's triangle starts with a 1, 1, 1, 1, 2, 1. Each term is the sum of the ones directly below that. If you think of this triangle of ones going down as swimming, it's just swimming in a sea, an ocean of zeros. So each of the ones on the sides are ones. And then these 3, 3, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Maybe this doesn't really seem all that related to what we're trying to do. What we're trying to do is expand this thing. But a fancy property of Pascal's triangle, if you're more interested in this, you can just look up Pascal's triangle. There are so many interesting patterns and relationships with Pascal's triangle. This line here, these are the coefficients of the expression when you expand this thing. So it's going to be, and then each term here is going to be, if you start with, if this is x and this is y, this is going to start out with x to the 5th, x to the 4th y, x to the 3rd y squared, x to the squared y cubed, x, y to the 4th, and finally y to the 5th. So really, x's start out big and go small, y's start out small and go big. So if we just put these coefficients here, 1x to the 5th, 5, 10, 10, 5, 1, that's how we would expand x plus y to the 5th. So when we plug in cosine of theta for x and I sine of theta for y, we're going to be able to expand it. So, mix this. What is the expanded version? If we set it, if this whole thing equals x to the 1, x to the 5th, so cosine to the 5th of theta, right? Okay. And then 5 plus 5, and then you've got cosine to the 4th of theta, and 1y there, so an I sine of theta, so 5i cosine to the 4th theta sine of theta. And you get to the point, we're just going to do this for all of these terms here, so plus another, I'm going to run out of space on this side, aren't I? So plus another 10 cosine cubed theta. And then you got a y squared, and this is maybe where it gets a little more interesting. It's a I squared is -1, so instead of a plus, it's a minus. And this is getting messy, and I don't even know if you can see this on the screen. But eventually, after you expand this whole monster, you're going to have some terms, see, that are with an I, some terms that are imaginary. And some terms, for example, this one and this one, there's a sine squared theta there. This one and this one, they're real numbers because they don't have an I in them. So the trick here is that we can pair them up, because remember, cosine of 5 theta plus I sine of 5 theta equals this whole thing. So we've got imaginary and we've got real. So we can set the real parts of the equation equal to each other, and we can set the imaginary parts of the equation equal to each other. But remember, we don't need I sine of 5 theta. We are trying to express cosine of 5 theta in terms of cosine of theta. So we're just going to match up the real part, cosine of 5 theta, with the real part over here. So, okay, let's get cracking. So cosine, I'm not going to do that here. I'm just going to erase this for now. Maybe not the best idea. So cosine of 5 theta is going to equal, okay, so this is real, cosine to the 5th of theta minus, okay, minus 10 cosine to the 3rd of theta sine squared of theta. I wish I'd written it all out before I erased Pascal's triangle, but I believe it's 1, 5, 10. It's 1, 5, 10. Excuse for the interruption here. 10, 10, 5, 1. Yeah, that's what I thought. Okay, 1, 5, 10, 10, 5, 5th, 4th, 3rd, 2nd. Okay, so we got it. So this was 10, corresponds to this one, and the next one plus, I believe, so x to the 5th, to the 4th, 3rd, 2nd, 1st, right? So plus 10 cosine of theta. If that's to the 1st, if it's going to be cosine to the 1 of theta, then that means it will be sine to the 4th of theta. Well, I sine to the 4th of theta. I to the 4th is just 1. So over here we're also going to have a sine to the 4th of theta. And then that last term is going to be imaginary. So cosine 5 theta equals cosine to the 5th of theta minus 10 cosine cubed of theta sine squared of theta plus 10 cosine of theta sine to the 4th of theta. So we've got it essentially, but we still have sines. We've still got sines in this whole expression. What can we do about those? Well, we do know that sine squared of theta, we know by the Pythagorean identity that sine squared of theta plus cosine squared of theta, we know that equals 1. So we can replace sine squared of theta, we can replace that with 1 minus cosine squared of theta. So my marker is fading on me. Times 1 minus 1 minus cosine squared of theta. Now what do we do with the sine to the 4th? Plus 10 cosine theta. Well, we could just say, I'm thinking here, 1 minus the cosine squared of theta is sine squared of theta. We square that and we're going to get sine to the 4th of theta. So over here, it's better. And cosine of theta, 1 minus cosine squared of theta squared. So that is cosine of 5 theta, and I am exhausted, yes. Cosine of 5 theta, and we now have to worry about that. Well, after expanding this whole thing, I'm not going to take you through all of the painful expansion here. After that, well, it's going to equal what? I'm just going to pause there. It's going to be 16 cosine to the 5th of theta minus 20 cosine to the 3rd of theta plus 5 cosine to the theta. And this cosine of 5 theta expressed in terms of cosine of theta is this. 16 cosine to the 5 theta minus 20 cosine to the 3rd of theta plus 5 cosine of theta. But of course, the result, while hopefully it is correct, matters a little less than being able to use the Moivre's theorem, because when we first learned this theorem, it's a pretty abstract thing. I mean, it's something that maybe you would have a harder time understanding how to apply it. But now we know that we can use it. For example, in this problem, when we had a form of cosine to the 5 theta, we wanted it to be purely in terms of cosine of theta. We wanted to get rid of that 5. So if you ever have cosine to the n theta, for instance, you can use de Moivre's theorem to get rid of that n. And there are a multitude of other ways that de Moivre's theorem can also be applied, and this is just one of those instances. Thank you.